Problem solving. The previous chapter suggested that decision-making is one of the major behavioral outcomes of the thinking process. Humans make many decisions, big and small, throughout the course of a day, a week, or a year. This chapter covers problem solving, which falls into the same category, that of major behavioral outcomes of the thinking process. When you are faced with some arrangement of physical or cognitive circumstances that do not quite give you what you need, you are being faced with a problem that needs to be solved. Problem solving is about taking the current state and transforming it into a goal state. Consider a problem that is faced by many university students. You need to arrive on campus in time for your 8:30 a.m. class, in which there is an exam. This is a pretty straightforward problem, but suppose on the morning there is a massive snowstorm that began in the early hours of the morning, which has affected many of the roads, bus schedules, closed the expressway you usually take, and has generally made things a mess. But the university is not closed. This presents a problem. Your goal is to get to the university at 8:30 a.m. in time for class. The current state is that there is an unusual amount of snowbound traffic, slowing or possibly blocking your route. You might solve the problem in a number of ways. For example, you could consult Google Maps for alternative routes. You could rely on general knowledge of the local city to bypass the usual expressway. You might check Twitter to try to pinpoint where the traffic is likely to be heaviest and look for a detour. You might also try to contact your professor to inform them that you are unable to drive in. In this example, the problem is the thing, snow and traffic, that interferes with achieving your goal. Solutions can be generated from memory, consultation, or examining the parameters of the problem in greater detail. And like many problems, there might not be a single best answer. The psychological study of problem-solving behavior attempts to understand how we represent and frame problems, how we select from different possible solutions, how we use our knowledge, and how we arrive at insights, objectives. On completing this chapter, you should be able to achieve the following: describe the basic steps in the problem-solving process, and be able to name and describe the different parts of a problem. Discuss problem-solving within Newell and Simon's problem space approach. Understand the importance of problem representation. Be able to explain what insight is and how people solve problems by insight. A general description. Parts of a problem. A problem is a gap or barrier between the initial or current state of affairs and the eventual goal. In order to be a problem, this gap or barrier is one for which there is no immediate route to a solution. In other words, if you know how to solve the problem, it's not really a problem. If you make coffee in your kitchen every morning, you likely already know the steps. So when there is a gap of time between the current state, no coffee yet, and the goal state, coffee, that might be a gap, but it is not a problem because you know how to get past the gap. The gap is not a problem in this case. Now what if you wake up in the morning and you are out of coffee? That's a problem. If you wake up and there has been a power outage and there is no electricity in the house, that's a problem too. Now the gap is less well defined and there is no immediate solution or way forward. Let's look more closely at the parts of a problem and see how problems are defined. Most problems have several features or aspects that define them as problems. A good working definition of a problem is that of a gap or a barrier between the current state and some goal state. I began the chapter with an example of needing to get to your early morning university class during a snowstorm. In this snowstorm example, the current state is being at home and the goal state is arriving at the exam on time. The problem is the snow and traffic congestion, which is a barrier between the current state and the goal state. In this example, the problem is something that impedes progression from the current state to the goal state. Figure 10.1 shows a schematic diagram of the components of most problems, including the current state and the goal state as the endpoints. Not all problems have these features, and in some cases the degree to which these components are either explicitly or implicitly designated can affect the difficulty and complexity of a problem. Figure 10.1, 5 parts or components of a problem. It is not necessary for all of these parts to be explicitly available to the problem solver. The degree to which a problem is well defined corresponds to how much of this information is explicitly defined for the problem solver. Okay, the diagram is called parts of a problem. So you have your givens, which go to your initial state, and then you go to obstacles, and you have means that feed into obstacles, and then you go from obstacles to your goal state. In addition to the goal state and the current state, problems also include givens. In problem solving, a given is an aspect, condition, and/or constraint that the problem solver must deal with when solving the problem. Think of these givens as tools or ideas that are given to you at the outset. These givens may frame the problem and suggest possible solutions. These givens may help or hurt the solving of the problem, but are not considered to be the gap that is the problem itself. In the winter storm example, suppose that you have a car and that you don't live near the bus line. In this case, one possible given would be the knowledge that you will have to drive to the university, rather than take public transport or an alternative means. This is a given because perhaps you already know that you have to drive because of geographic reasons. This fact is information given to you that affects the way you see the problem and the way you approach the problem. As such, it places constraints on the possible solutions and how the problem could be solved. Givens can be explicit or implicit in nature. Needing to drive is an implicit given. It was not stated explicitly in the original problem, but it is an implicit aspect of the situation. Consider another example. In the USA and Canada, and probably in other parts of the world, many people enjoy watching competitive cooking shows on TV. A popular show during the time I was writing this chapter was Chopped. In this show, contestants must create a dish in 20 or 30 minutes from a set of idiosyncratic ingredients. The ingredients are not revealed until the timer starts. In this case, the givens are the ingredients, the standard cookware, and the set of staple ingredients that each contestant receives. These are all possible means to solve the problem that are literally given to the contestant. All of these things can either inhibit or facilitate solving the problem of creating a winning dish. Unlike the winter storm example, many of these givens are explicit and known to contestants when they begin. Figure 10.1 also shows the obstacles, which are at the heart of a problem. The obstacles are the things that interfere with the direct path between the current state and the goal state. In the winter storm example, of course, the obstacles are unexpected snow and traffic on the main route. In the chopped example of being asked to cook a meal from some new ingredients, the obstacles are the short time frame. In the show, it is 20 or 30 minutes, as well as being unfamiliar with how the ingredients should combine. Obstacles may seem more difficult and more challenging under cognitive limitations like time pressure, multitasking, and evaluation. As we discussed earlier in Chapter 3 on knowledge and working memory, anytime a person is required to perform multiple cognitive tasks, their performance on any one of those tasks can be negatively affected. This presents an additional problem. Sometimes the impact of an obstacle can be reduced or almost eliminated when the problem solver is very familiar with the problem context. Experts, for example, may be able to retrieve a possible solution from memory. This greatly reduces the cognitive load. In other words, rather than try to solve the problem by working towards a novel or unexpected solution, the expert solves the problem by recalling a possible solution from memory in prior experience. Consider expertise with respect to the winter storm example. If you are very familiar with traffic patterns and with your city, you should be able to come up with a detour that may solve the problem with less effort than would be required by someone with no knowledge of the local geography. There is still a problem to solve and still a gap or barrier, but you can rely on a heuristic approach via System 2 to retrieve a possible solution from memory. Or consider expertise with respect to the cooking show example. If a contestant happens to receive ingredients that they are very familiar with, then they can retrieve from memory appropriate ways to combine those ingredients to make an exciting final dish. In general, experts tend to rely heavily on memory retrieval when solving problems, rather than rely on some of the problem-solving heuristics that will be discussed later in this chapter, and this tendency has often been described as one of the cognitive hallmarks of expertise. Expert thinking will be discussed in much greater detail in the final chapter. The initial and goal states, the obstacles, and the givens are all aspects of the problem itself. But what about the steps a person takes to actually solve the problem? These steps are known as means. You might know a familiar expression, means to an end, that refers to the steps taken to reach a conclusion. As shown in Figure 10.1, the problem-solving means act on the obstacle or obstacles. The means are the operations that are used to change the original state and move closer to the goal state. Means can be cognitive operations, such as mental imagery, verbalization, or memory retrieval. Other cognitive means are imagining the problem from a different perspective, imagining the solution, or representing the problem in a different way from how it was originally posed. For example, when given a set of ingredients on a competitive cooking show like Chopped, contestants often proceed in one of two ways. Some start with a final dish in mind and work backwards to decide how to process the ingredients to get that final dish. Others will occasionally not know what to do with an ingredient. They may begin working on one ingredient without a final dish in mind. Both of these contestants are trying to solve the problem, but with different means. Well-defined and ill-defined problems. It should be evident from the examples given above and the description of the components of a problem that problems can vary in terms of how clearly defined they are. A problem with completely specified initial states and goals, well-articulated givens and obstacles, and a specified means of attaining that goal or goals can be considered a well-defined problem. An example of a well-defined problem is a multiple-choice problem on an exam. The question is clear, the options are clear, and the goal is to select one correct answer. There is very little ambiguity in terms of what is required. Another example would be cooking a batch of brownies from a recipe. A well-written recipe instructs the cook on what ingredients are needed, how many and how much are needed, how to combine them, and often includes a picture to show what the final result should look like. Cooking something from a recipe is a well-defined problem. If one or more of the aspects of the problem is missing or not defined, the problem can be considered an ill-defined problem. For examples of ill-defined problems, consider many of the problems that university students and college students are often faced with. If your goal is to obtain a good mark in a given course, it may not be clear what the initial state is, even though the goal state is clear. Furthermore, the givens, constraints, and means may not be very well specified. Additional obstacles may arise during the course that make it more difficult to obtain a good mark in the class. Other examples would include investing money, troubleshooting your computer when it seems to be acting sluggishly but you are not sure why, or writing an essay for a class without an assigned topic. These are all problems because there is a gap between the initial and the goal state. But in each case, there may be some aspects that are defined and other aspects that are not defined. In general, most problems exist between the two endpoints of being well-defined and ill-defined. Problem representation. Solving a problem often requires the creation of one or more mental representations. A problem representation is a mental representation constructed by the problem solver to assist in solving the problem. The representation can help to clarify the end states as well as the givens and obstacles. In addition, solving a problem often involves changing an ill-defined problem into a well-defined problem by changing the nature of the representations. For example, we have been discussing the nature of problem solving in competitive cooking shows. The problem of being given several ingredients and then being asked to create a signature dish can be represented in at least two ways. In one case, the representation focuses on the ingredients and how to transform them. An alternative representation focuses on the final dish and how to incorporate those ingredients into a final dish. Although either of the representations may result in an excellent final dish, it is possible that switching from the ingredient-focused representation to the final dish representation, or the other way around, can assist in solving the problem. In other words, would the problem be easier to solve if you focused on what you wanted to create or how you wanted to create it? An example by Posner makes the point more systematically with respect to an ill-defined problem and two possible ways to represent the problem. In the birds and trains problem, the initial statement and representation seems very difficult and nearly impossible to solve. Two train stations are 50 miles apart. At 2 p.m. one Saturday afternoon, the two trains start towards each other, one from each station. Just as the trains pull out of the stations, a bird springs into the air in front of the first train and flies ahead to the front of the second train. When the bird reaches the second train, it turns back and flies towards the first train. The bird continues to do this until the trains meet. If both trains travel at the rate of 25 miles per hour and the bird flies at 100 miles per hour, how many miles will the bird have flown before the trains meet? On the surface, this seems like a very difficult problem to solve. First, there are some possibly extraneous details like the time and day. Second, the problem itself focuses attention on the bird, as the speed of the bird is the unknown that we need to solve for. Oh, we already know the speed of the bird. I think that's a typo. The statement of the problem, how many miles will the bird have flown, frames the problem in terms of the bird, and it's probably the most obvious representation. In other words, if the problem is framed this way and represented in terms of the bird's flight distance, the problem solver will be tempted to try to solve it this way. Solving the problem in this way would mean trying to calculate many simultaneous equations that keep track of the trains moving towards each other and the cumulative distance of several back and forth flights by the bird, each one shorter than the last. It might not be impossible, but for all practical purposes, it probably is. On the other hand, it is possible to solve the problem by focusing on the trains and the stations. Figure 10.2 shows two possible representations. Figure 10.2, Posner's bird and train problem. This illustrates the importance of proper problem representation. The problem is nearly impossible to solve if the solver focuses on the bird and builds a representation accordingly. A representation that focuses on the train is much easier to solve. Bird and train problem. A representation that focuses on the bird is difficult to solve. So it shows the two trains coming at each other from different directions and the bird, like the vectors of the bird flying back and forth between them. B, a representation that focuses on the trains is easy to solve. So you can see the trains are coming toward each other from station 1 and station 2, and they have to go 25 miles to get to the bird in the center from either direction, and the total distance is 50 miles. At the top is an example of the complexity of solving the problem from the perspective of the bird representation, which is likely to be the initial representation that problem solvers adopt. At the bottom is a relatively straightforward way of solving the problem from the perspective of a train-focused representation. The train-focused representation takes into account the distance between the two stations, 50 miles, and the rate of speed of the trains, 25 miles per hour. With that information, you know the two trains are going to meet halfway at 25 miles. The time it takes each train to travel the 25 miles at the rate of 25 miles per hour is 1 hour. Notice that the bird's speed is 100 miles per hour. According to the initial statement of the problem, the bird will have been flying back and forth many times for the entire hour. If the bird is flying back and forth for an hour at a rate of 100 miles per hour, it implies that the bird will have flown exactly 100 miles. This representation ignores the bird until the end. It also ignores the potential pitfalls of figuring out how many back and forth trips it takes. It doesn't matter how many trips back and forth the bird has taken. All that matters is that the bird has been flying for 1 hour at a rate of 100 miles per hour. Posner's bird and train problem underscores the importance of the correct representation. This problem seems difficult at first, but when approached in a different way with an alternative representation, it can be very simple. So the initial question is, how many miles will the bird have flown before the trains meet? And because the bird flies at 100 miles per hour and they're flying for an hour, they will have flown 100 miles. So in fact, the given already solves the problem. Stages of problem solving. Problem solving can be fairly easily divided up into 4 stages. These stages may not occur in every case, and certainly if the problem is being solved by an explicit memory retrieval of a previously solved problem, then some stages might be skipped. Notice that these stages are similar to, but not exactly like, the states of decision-making that we discussed in Chapter 9. The parallel is unavoidable because when we have to do some thinking work, judging, deciding, problem-solving, we tend to follow the same stages to recognize the current state, frame it, try to bring knowledge to bear, generate alternatives, and assess the viability of those alternatives. The first stage can be referred to as the preparation stage. In the preparation stage, the problem solver first understands that the problem exists, evaluates the presence of any givens, the presence of an initial state, and frames the problem. At this stage, the problem solver would also examine any constraints and try to understand the eventual goal. The problem solver might try to estimate how long it will take to solve the problem and/or what resources would be needed. In this stage, a well-defined problem and an ill-defined problem can be differentiated. In the production stage, the problem solver begins to generate, produce, and work on potential solutions. Many of these could be the result of general-purpose problem-solving heuristics, such as the hill climbing, means end, or working backwards strategies that will be discussed later in this chapter. In addition, if prior knowledge is brought to bear, or if previous examples need to be recalled, it is likely to take place in this production stage, which happens right after the problem is realized. The means are generated and applied. The ongoing success is monitored. The utility of shortcuts and heuristics is occasionally reconsidered. As potential solution paths are generated, the problem solver engages in the judgment or evaluation stage. In this stage, tentative solution paths may be explored further. They may be evaluated for the likelihood of success, and if no correct solution is applicable, the problem solver may give up and stop working on the problem or persist. The problem solver is also monitoring the similarity between the current state and the goal state. If the current state matches the goal state, then the problem is solved. In many cases, an additional stage, referred to as the incubation stage, may occur even if the problem solver gives up or moves on to another task. During the incubation stage, spreading activation in semantic memory may continue. See Chapter 3. In other words, even if the problem solver is no longer explicitly trying to solve the problem, there may be implicit associations being drawn. Sometimes a problem is only solved by putting it out of mind or by working on something else. Upon returning to the problem, the solution seems evident. This sometimes results in an insight, which may have physiological correlates related to a feeling of satisfaction or relief. Insight problems will be discussed later in the chapter. The psychological study of problem solving. The study of problem solving from a psychological perspective began in earnest in the Gestalt era. I covered some of this in Chapter 1 on historical approaches to the psychology of thinking. For example, Karl Duncker, whose influential work on functional fixedness will be covered later in this chapter, published a book on problem solving in German in 1935, which was later translated into English. This work covered the general description of what makes a problem, the components of problems, the importance of problem representation, insight, and functional fixedness. Max Wertheimer, another of the major figures in the Gestalt era, was also heavily involved in problem-solving research. His book Productive Thinking covered the topics of problem-solving and representation, 1959. Although psychology in North America was heavily invested in the behaviorist paradigm, which did not address problem-solving very well, the work of the Gestalt psychologists in Germany helped to lay the foundations for the modern cognitive approach. Within the modern era of cognitive psychology, and more recently cognitive neuroscience, a key starting point was the publication of Human Problem Solving by Newell and Simon, 1972. Newell and Simon approached the study of problem solving as cognitive scientists. Their goal was to explain in precise detail the general problem-solving strategies that humans use. As cognitive scientists and also computer scientists, Newell and Simon were especially interested in how one might instantiate a set of problem-solving heuristics or algorithms via a set of computer instructions. At the time, a common way for a computer to carry out tasks and execute instructions was to ask the program to search through stored information and stored bits of instruction, kind of like searching through a physical space to find the solution. In the same way, Newell and Simon then defined problem solving as a search through the problem space. Their problem-solving theory is known as the problem space approach. Central to this theory is the metaphor of physical geometry in problem solving. Conceptual metaphors can be very useful in a complex domain like problem solving. Recall from Chapter 2 on similarity that we discussed a geometric approach to similarity that made a similar metaphorical link between psychological space and physical space. The problem space approach assumes that the solving of a problem requires navigation through the problem space. The problem space is the representation that encompasses all of the possible solution steps. One region of the space represents the initial state, and the other region of the space represents the goal state. Much like the very simple mazes that you may have done as puzzles when you were a kid, problem solving requires finding the shortest path from the initial state to the goal state through the problem space. Various operators can be employed to reduce the path, and representing the problem in a different way might reveal a shorter path. And just like searching for a solution in physical space, searching for a solution in a problem space may involve branching paths and making a decision to choose one of the paths. As described earlier, the problem space approach grew out of Newell and Simon's artificial intelligence research. Concurrent with trying to understand how humans solve problems, they were also interested in trying to design a computer algorithm or computer program that would be able to solve general problems. They refer to this idea as the general problem solver. One of the limitations of a computer problem, of course, is that it may not have the extensive background knowledge and subject expertise of human problem solvers. As a result, their approach emphasized problem-solving algorithms and problem-solving heuristics. Many of the ideas in Newell and Simon's problem-solving approach were first discovered by an analytic technique known as protocol analysis. Newell and Simon conducted several studies in which problem solvers were asked to think out loud while solving a problem. The general idea is that it can be very difficult to figure out all the small steps that take place between the initial state and the goal state. This can be especially problematic if the problems are being solved quickly, or if the problem solver considers several things in parallel before commencing with the solution. By asking subjects to think out loud, it is possible to gain some insight into these intermediate states. The downside to thinking out loud is that it can interfere with problem-solving strategies. Thinking out loud interferes with general working memory capacity and may also interfere with executive functions. As we discussed in Chapter 3, Executive functions mediate many of the complex switching behaviors and goal-oriented behaviors in cognition. As an example, you know how easy it is to solve basic arithmetic problems, and in many cases you take shortcuts. If you have to stop and think out loud at every step, it is going to slow you down. As another example, I have been using competitive cooking TV shows as a way to illustrate parts of a problem. In these sorts of shows, the cooks or contestants are often talking out loud, but most of the commentary comes from interviews that were taken after the actual competition, which are then spliced into the production. It is much more difficult to think out loud when you are doing something stressful than it is to comment about it afterwards.